Am I audible? Hello? Can anybody please tell me if I am audible or not? Hello? Am I audible? Please let me know if I am audible or not.
We can hear you.
Okay. Let's wait for a couple of minutes. After that, I will start. Let's wait for 5 minutes.
Okay.
Hmm. बोल. हाँ, आज गेम है आपका? आज गेम छोड़ के अब खेलने आप मूवी देखने जा रहे हो? ठीक है वो तो मैं ऊपर आऊँ. ठीक है. Okay, so we may start now. Please let me know if you can see my screen or not. I believe you can see my screen. So, welcome to the NPTEL live session. Today is our fifth session, and in the last session, we discussed about beams on elastic foundations, infinite beams, semi-infinite beams. I solved some problems regarding all those things, and I believe you have understood them. In today's session, I'm going to discuss about some design of shallow foundations. So today I'm going to discuss about design of shallow foundations. Design of shallow foundation means we are going to find out the dimensions. I'm going to show you how to find out the dimensions of the shallow foundations using in situ tests, using in situ test data like SPT, CPT data, or maybe using lab test data. Okay, so let's go to the first problem. Let's see what is the problem. So this is the first problem. Using Peck Hansen, this will be Hansen actually. Peck-Hansen-Thornburn 1974 procedure determine the allowable bearing pressure QA net for an isolated footing of width 3 meter. The depth of foundation is 1.5 meter. The water table is 1.5 meter below the ground level. Average corrected SPT N value is 23 and permissible settlement is 50 millimeter. So we need to use the Peck, Hansen and Thornburn 1974 method. So we need to use Peck, Hansen and Thornburn 1974 method. By using the method, we will find out net allowable bearing pressure that can act the net allowable bearing pressure for an isolated footing of width 3 meter. The depth of the foundation is mentioned, which is 1.5 meter. The water table is 1.5 meter below the ground level, and average SPT value is 23, and permissible settlement is 50 millimeter. So, what is this? This procedure of Peck, Hansen, and Thornburn 1974. Well, according to Peck, Hansen, and Thornburn, they have given a formula, a equation for net allowable bearing pressure for isolated footing. Let me write down the formula, okay, for the isolated footing. So qa net is equal to 0.044 cw, which is the correction for the water table. N is the SPT value, and SA is the permissible settlement, which is 50 millimeter. This one, and the unit of this will be in ton per meter square. So first of all, let me draw the problem. So there is an isolated footing. The width of the footing is 3 meter, and if this is the ground surface, the depth of the footing is 1.5 meter. This is the depth of the foundation, df, and the water table is 1.5 meter below the ground level. That means the water table lies over here at the base of the foundation. This is the water table, ground water table, and average SPT value N is 23, and permissible settlement SA is 50 millimeter. So we have the formula here over here. This is an empirical equation given by Peck, Hansen and Thornburn. So 0.044 CWN into SA. CW is the water table correction. We need to find that out. So what is the water table correction? CW for Peck, Hansen and Thornburn. So the correction for the water table is, there's the equation which is 0.5 plus 0.5 into dW, which is the depth of the water table, divided by dF plus d. This is the water table correction. So now let me put all the parameters, the values of all the parameters. So 0.5 plus 0.5 into what is dW? What is the depth of the water table? It is 1.5 meter, right? It is 1.5 meter. So dW is 1.5 meter. So into 1.5 meter divided by what is the depth of the footing? Depth of the footing is also 1.5 meter. The depth. So 1.5. And what is the breadth of the footing? Breadth of the footing is 3 meter. So 3 meter. See, all the parameters are in meters, okay? So now if you calculate this, you will get 0.67. This is the correction for the correction for the water table. Okay, so now we have the value of CW, and also we have the value of N. What N is the the average SPT value, and we have the value of permissible settlement, which is 50 millimeter. Okay, now let us put all the values of all the parameter into equation. Let me mention one thing. This CW, it has no unit, it is unitless, because you see 0.5 plus 0.5 into 1.5 meter divided 1. Both of these are in meters, so it is just unitless. So and this n will be in n also that doesn't have any unit. It is the blow count, average SPT value, and S is the permissible settlement, and that should be in millimeter. Okay, now this is an empirical equation. Okay, so you need to put if you put all the parameters and SA in terms of millimeter, if you calculate this equation, you will get the value, and the uh, result will be, and the unit of the result that you will get will be, the unit will be ton per meter square. Okay, so now let me put all the values. So qa net is equal to 0.044 cw in SA. This will be in ton per meter square, meter cube, meter square, sorry. Now, okay, so here it is. So let me write down the equation once again. So it is 0.044 into CW into N into SA, and this will be in ton per meter square. SA is in millimeter, and that's all. Okay, and this too has no unit. Okay, so now let me put all the values over here. So 0.044 into CW. What is CW that we got over here? It is 0.67, 0.67. N value is, the value of N is 23, 23. And what is the permissible settlement, allowable settlement? It is 50 millimeter. Okay, now if you calculate this, if you calculate this, you will get qa net will be 34 ton per meter square. Okay, remember one thing, this permissible settlement will be always will be in millimeter. Okay, and you will get the answer in terms of ton per meter square. Remember this. Okay, so the answer is 34 ton per meter square. So if you have any doubt in this question, you may tell me, or else I will proceed to the next question. So have you all understood this question? This is a very simple problem. Just we need to use the empirical equation. And we also, there is also another empirical equation to calculate the water table correction. We need to incorporate all those things in order to find out the qa net. So I hope you have all understood this problem. Now let me just proceed to the next question. So this is the next question. So what is the question? So
Hello,
during,
good evening, sir.
yes, tell me.
Sir, please proceed the previous question, sir.
Okay, tell me, what problem do
Once
you
again,
have?
repeat again, sir. Sir,
Okay.
CWNSSA.
CW. What is
Please.
CW? It is
Yes.
the groundwater table correction. Okay, you need to find out the groundwater table correction using a formula. See, there is a
Okay,
equation.
sir.
There is a equation CW equal to 0.5 plus 0.5 into DW divided by DF plus B. This equation was also given by those Peck, Hansen, and Thornburn. So they recommended to use this equation along with, if you want to find out the net allowable bearing pressure, you need to also use this. Okay, correction for bearing capacity, correction for groundwater table. So you need to find out this CW, that is the correction for the groundwater table. So that is 0.5 plus 0.5, and DW, what is DW? It is the depth of the water table. So see in this diagram, the depth of the water table lies over here. So the depth of the water table is 1.5 meter, and the depth of the footing is also 1.5 meter. So see, the water table lies at the base of the footing. So I have just put whatever there is in the question. I have just put all the values of all the parameters in this equation. If you just calculate after putting all the values of all the parameters in this equation, you will get 0.67. CW as 0.67. Okay, now after finding out CW, you need to put all the parameters that you have. That is CW, N is the SPT value you have that, which is 223. It is mentioned in the question. And SA is the permissible settlement. You also know that it is 50 millimeter. So now if you just put all the values of all the parameters into this empirical equation, you will get the value that is the net available pressure in terms of ton per meter square. Okay.
Okay, sir.
Okay. So I hope you have understood this problem.
Yes, sir. Yes.
Okay, so let me proceed to the next question. So during the design of an isolated footing, dimensions of 2 meter by 3 meter. First of all, let me write down all the data which is given in the question. So breadth is 2 meter, length is 3 meter, and the footing is placed at a depth of 1 meter in the clay soil. So the depth of the footing is also is 1 meter, and the soil is clay. Footing is subjected to a load of 100 kilonewton. Fine. Load is 1000 kilonewton. Sorry, 1000 kilonewton. The clay stratum is 10 meter thick, underlain by a hard stratum. Okay. The clay soil has the following properties. That is, the gamma sat is given, gamma bulk is given, compression index CC is given, CU, that is the underend cohesion, is also given. Initial void ratio 0.7 is given. Unit weight of water, okay. The pore water pressure and depth correction factor is also given. The water table is at a depth of 1.1 meter below the ground level, or the clay surface. So, compute the consolidation settlement of the footing after applying all possible settlement correction. Neglect immediate settlement. And okay, so we need to find it out. And so you need to find out the consolidation settlement, and the distribution of stress is 1 is to 2. 1 is to 2. Here 1 is to 2 means 1 horizontal is to 2 vertical. I will show you how to solve this problem. So first of all, let me draw the problem. So the breadth of the footing is 2 meter, and the footing is placed at a depth of 1 meter. So this is the footing. The breadth is 2 meter. So the breadth is 2 meter, and it is at a depth of, what is the depth of the footing? The depth of the footing is 1 meter. 1 meter in a clay soil. So the depth of the footing is 1 meter, and the footing is subjected to a load of 1000 kilonewton. Okay, fine. So 1000 kilonewton load is coming, 1000 kilonewton. The clay has the following properties: gamma sat, gamma bulk, compression index, Cu, all those things are given. The water table is at a depth of 1 meter below the ground level. So that means water table is at the base of the footing. Water table is at the base of the footing, ground water table. Fine. Ground level. The water table is at a 1 meter below the ground level or clay surface. Compute the consolidation settlement of the footing after applying all possible settlement correction. And distribution of stress is 1 is to 2. Okay, so first of all, what is the influence zone for the settlement? Okay, in order to find out the settlement of such problems, we need to first know what is the influence zone for these types of for settlement case. Actually, for let me just tell you once. let me just tell you one thing. Influence zone. Okay, so that means how much influence, how much zone we must consider for such problems. So influence zone for bearing capacity problems, in order to find out bearing capacity, bearing capacity or bearing pressures, all those problems, for those types of problems, influence zone is 2b, 2b below the base of the footing. Okay, that means from here to somewhere over here, 2b. Okay, and for settlement problems, that means if you want to find out the settlement of this footing, for such problems, influence zone is b, that is b b distance from the base of the footing. Okay, so for bearing capacity problems it is 2b, for settlement problems it is b. So now let us solve this problem. So what is happening over here? So what is the value of 2b? So value of 2b is 4 meter, right? 2 into the breadth is 2 meter, so 2 into 2 is 4 meter.
Yeah, 2 crore.
Okay, so 4. So we need to consider up to this layer. Okay, up to this boundary actually, up to 4.
Sir, this is the weight zone. Yeah?
Yes. What?
Sir, it is weight zone.
It is wet zone. You see, this is completely
Yes,
dry.
sir.
This is completely dry, and this water table is over here, and this is below the water table. Yes, this is saturated, totally submerged condition. Okay, this part is totally submerged. See, water table is over here. So we need but the influence zone we need to consider. The influence zone for bearing capacity problems is to be below the footing. Below the footing, we need to consider influence zone up to a distance of 2b from the base of the footing for bearing capacity problems. But for settlement problems, we need to consider up to b. So now how to solve this problem? So influence zone is around 4 meter from the base of the footing. Okay. Now we need to find out the distribution of stress. Okay, and also for those and for such problems we need to consider bear capacity. We need to find out over here actually the surcharge and the distribution of load. We need to find out the overburden pressure acting at this point, that is half of 4 meter, that is up 2 meter. So what we have done, we have found out what is the value. We have found out the distance of 2b from the base of the footing. Now we are just dividing it into two parts. Okay, so we need to find out the overburden pressure acting at a depth of 2 meter from the base of the footing, and also we need to find out the stress distribution due to this 1000 kilonewton. So let me just write it down. Let me just show you how to do that. So first of all, let me just find out the overburden pressure, that is P0. Okay, so effective overburden pressure, so this part, the top part is completely dry, so dry or maybe partially saturated, something like that. So what unit weight should we use for the top part? We must use bulk. Okay, the bulk unit weight, that is 16. So what is the thickness of that layer? It is 1 meter. 1 meter, that is the part above the groundwater table. So now we are finding out the overburden pressure at this point. Let me just term this at A, this point, A point. So it will be 1 into 16, 1 into 16 plus this portion, thickness of this portion, that is 2 meter, multiplied by the submerged unit weight of this portion. So submerged unit weight means gamma sat minus gamma w. So what is gamma sat? Gamma sat is 18 and gamma w is 10. So gamma sat is 18 minus gamma w is 10. Okay, multiplied by the thickness of that layer, that is 2 meter, so into 2. Now if you solve this, you will get overburden pressure at point A, it is 32 kilonewton per meter square. Let me know if there is any calculation mistake. Please solve this problem along with me. So 32 kilonewton. So 32 kilonewton is the effective overburden pressure at this point. Okay. Now let me just find out the distribution of stress due to this 1000 kilonewton. It is mentioned over here. It is mentioned over here that the distribution, the stress distribution is 1:2. 1:2 means one horizontal, two vertical. So actually, it is happening like that. We must consider up to this half of 2b, that is up to b. So it is happening like this actually. See, the slope is 2:1. 2 vertical is to 1 horizontal. See, the stress is distributing like this. See, this is the footing. Footing is rectangular. I believe it is 2 by 3. 2 meter is breadth and length is 3 meter. This is the footing. And the stress is distributing like this. Okay, it is distributing like this, like 2:1 ratio, 2 horizontal, 2 vertical is to 1 horizontal, like this. So now we need to find out the effective area at this point. Okay, the effective area. So what is the effective area at this point? What will be the length? We know the breadth of the footing is 2 meter. So, and the height of this portion is also 2 meter. So what will be the length of this portion? So this is 2:1. That means if this portion is 2 meter, this one will be half of 2. Okay, 1 meter. And this portion, the length of this portion will also be 1 meter. So what will be the total length? Total length, okay? Total length from this point up to this point. What will be the total length? It's 2 plus 1 plus 1. So that means the new length will be 4 meter, new breadth actually. So
Yes, sir.
new breadth is equal to 4 meter. So have you understood how it is coming? 4 meter, okay? So for the length case, same thing is happening. In if you just turn the footing around, if here the breadth is 2 meter and another side there is length, the another here see, this is the front side. If you look the footing from the sideways, you will see the length which is 3 meter, and same distribution is happening. Okay, so what will be the new length of the footing? New length of the footing will be similar, that is 3 plus 1 plus 1. The this distance is same, so this one will be 1, this portion will also be 1, but from sideways you will get length. So the length is 3 meter in that case. So 3 plus 1 plus 1, that means 3 1 plus 4 for 5. So new length will be 5. If you have any problem in this concept, please let me know. See, I am drawing it once again over here. See, this one is breadth, and if see how does the footing look like? Footing looks like this. This one is breadth, this one is length. Okay, and same thing is happening. Distribution is happening like this, both the cases. So if the new breadth is, the new breadth is 4 plus 2 plus 1 plus 1, the new length will be also like this, na? 3 plus 1 plus 1. So 3 plus 1 4 and 1 5. So have you understood this, how it is coming?
Yes, sir.
Okay, so now what is the so what is the stress at this position at point A? Stress due to this 1000 kilonewton. So stress due to 1000 kilonewton, we must denote it by using del P, because it is the additional stress. Additional stress means it is the stress apart from the overburden pressure that was originally acting. Overburden pressure that was initially acting is 32 kilonewton per meter square. Now we are just adding additional load. So additional load is 1000 kilonewton, and due to this additional load, what stress is what, and we need to find out how much stress 1000 kilonewton is causing at point A. So 1000 kilonewton. So del P is the additional stress that is being caused by the 1000 kilonewton. So that is 1000 kilonewton divided by area. What will be the area? That is B dash L dash. So 1000 divided by 4 into 5. Now if you calculate this, you will get del P is equal to 50 kilonewton per meter square. Okay. So we have all the we have now we have the values of all the parameters that are required to find out the consolidation settlement. Okay. So we have been asked to find out the consolidation settlement. So what is the formula for the consolidation settlement? So we need to, so what is the formula? Wait for a minute, please. So I hope you are able to see my slides. So so 1000 divided by how much it was? It was 4 into 5. So if you calculate this, the additional stress that 100 kilonewton, that 1000 kilonewton was causing at point A will be 50 kilonewton per meter square. Okay, so now we need to find out the consolidation settlement. So what is the formula for consolidation settlement? AC is equal to CC, that is the compression index, divided by 1 plus initial void ratio multiplied by thickness of the layer into log to the base 10 P dash, that is the overburden pressure, initial overburden pressure, plus the stress, additional stress that is acting after applying the load, divided by effective overburden pressure. Okay, effective initial overburden pressure. So now let me just put all values of all the parameters into this equation. So what is the value of Cc? The compression index. The compression index is how much it is? Compression index is 0.18. So compression index is 0.18 plus 1 plus is 0. So what is the value of initial void ratio? Initial void ratio is 0.7. So 0.7 into h. What is the thickness of the layer? What is the thickness of the layer? The thickness of the layer in this case, see, in this case we found out the effective overburden pressure at point A and also the stress distribution at point A at 2 meter below the base of the footing, that is half of 2b. But what was the original layer? Original layer, see, the original layer was over here. Original layer was 10 meter thick. Okay, but what was the influence zone? The influence zone for this problem is 2b. Okay, so for consolidation settlement, this h will be up to the influence zone. Okay, that means 2b. So what is b over here? What is b over here? It is 2 meter. So influence zone will be 2b. So that means h is equal to 2b. That means 4 meter into log to the base 10 P0. What is P0? That is the initial overburden pressure. It is 32 kilonewton per meter square. plus del P, that is the additional stress, that is 50 kilonewton per meter square, divided by initial overburden pressure, that is 32. Okay. So now if you calculate this, you will get, and obviously you must multiply this equation with 1000 to get the answer in millimeters. This 4 is in meters, so you will get this answer in meters. And if you just multiply this equation with 1000, you will get the answer in millimeters, which is 173.1 millimeter. Okay, 173.1 millimeter. This is the consolidation settlement. Okay, but here another thing is given. Pore water pressure and depth correction factor is 0.7 and 0.88 respectively. So we need to incorporate these correction factors also. So the settlement here is 173.1. We need to just multiply the correction factors with this settlement. Okay. So final settlement or the corrected consolidation settlement will be 173.1 millimeter into the correction factors, that is 0.7 and 0.88. So 0.7 and 0.88. If you calculate this, you will get the correction factors. You will get the consolidation settlement. The consolidation settlement will be 107 millimeter. Okay. So here we have just multiplied the correction factors with the consolidation settlement which we got from this equation. Okay, so if you have any problem in this, if you have any doubt in this question, please let me know, or else I will proceed to the next question. The only important thing in this question is how to calculate the additional stress. Actually, you need to just take care of this distribution of stress, how the stress is distributing. Okay, like this, how the stress is distributing along breadth and length. You need to just find out that. The rest is very simple. You need to just use the equation and you will get the answer. So if you have any problem in this question, please let me know. So I believe you guys don't have any problem in this question. So let me just proceed to the next one. So what is the next question? Using Teng's 1962 correlation, determine the net ultimate QNU, that is the net ultimate wearing capacity of a square footing of dimensions 3 meter by 3 meter resting on sandy soil. Okay, so here is a square footing of dimension 3 meter by 3 meter resting on a sandy soil. We need to find out the net ultimate wearing capacity of the footing. So corrected SPT values are given over here. Depth of the foundation is also given over here, which is 1.5 meter below the ground surface. Water table correction RW is 1 and RW dash is 0.65. Okay, I will explain all those factors, water table correction factors. And one thing, the equation is given. Okay, the equation for net ultimate wearing capacity, Teng's equation. This equation was given by Teng in 1962. So this is the equation. So let me just write down one thing. Teng 1962. Teng in 1962 gave two equations. Okay, one was for strip footing, another one was for circular or square footing. So for strip footing, the equation is 1 by 6 3n square b into rw plus 5 into 100 plus n square into df into rw. This equation is for strip footing. Okay, and for square footing or circular footing, The equation is this. Let me write down the equation once again. Circular or square footing. So what is the equation? Q into Nu equal to 1 by 3 n square b here w dash. This one will be dash actually. So n square b r w dash plus 3 into 100 plus n square df into rw. So this is the equation for circular square footing. So how to calculate, how to find out these factors? What are table correction factors? It is already given over here, but how do you find out this? Okay, how to find out? So there is a graph. You can find it out in any book. So this graph actually, okay. So in order to find out RW, in order to find out RW, we must use dw by df ratio, and for rw dash we must use dw dash by v ratio. So what is dw and dw dash? Let me just draw it once. So suppose this is a footing over here, and the groundwater table, suppose this is the ground surface and the groundwater table is somewhere over here, okay, above the base of the footing, mind it, okay. And in another case, suppose in this case, this is the ground surface and the water table is somewhere over here. So in the second case, suppose the water table is somewhere around here below the base of the footing, okay. So what is dw? Dw is the depth of the water table. So this one is the depth of the water table above, depth of the water table above the base of the footing, okay. And what is dw dash? dw dash is the depth of the water table from the base of the footing, that is from over here. This is dw dash. So what is dw? It is the depth of the water table from, it is the depth of the water table above the base of the footings, and this one is the depth of the water table. This is also the depth of the water table, but in this case the water table lies below the base of the footing, and the depth is taken from the base of the footing to the water table, okay. So that is dw dash. So we need to use dw and dw and so we need to use this ratio dw by df in order to find out rw from this graph, and we need to use dw dash to and b, the ratio between dw dash and b, in order to find out rw dash also from this graph, okay. So one thing we must one thing you must know one thing you must know, suppose the water table, this groundwater table is over here. Groundwater table, suppose the groundwater table is at the surface. So in that case, dw dash will be 0. No, sorry. So no, yes. If the groundwater table is over here, that means dw will be 0, right? Dw will be 0. Okay, so forget about that. If the groundwater table is over here at a depth dw, that is above the base of the footing. So this is the base of the footing, and the groundwater table is above the base of the footing. In that case, this dw dash will be 0, right? Because dw dash is taken below the base of the footing, okay. Below the base of the footing, the depth is taken from the base of the footing to the groundwater table. So if the groundwater table is above the base of the footing, so in that case we will get some value of dw, but dw dash will be 0. So in that case dw dash will be 0. So what will be the ratio of rw dash in the first case? For the first, this one is the first case, this one is the second case. For the first case, you will get the value of dw by df, because dw you will get a positive value, but dw dash will be 0, right? So what will be the value of rw in that case? Dw dash will be 0. So corresponding, if you find out dw dash by b ratio, that will be 0. So corresponding rw dash will be 0.5. See, at this point is rw dash is 0.5. Okay. And suppose if the depth of the if the foot if the water table lies at the base of the footing, if the water table is at the base of the footing, that means dw is equal to df, right? If the water table is at the base of the footing, that means dw is equal to will be equal to df. If dw is equal to df, that means rw will be equal to 1. 1 means this ratio will all this rw will be 1 actually. Okay. dw by df, if dw by df is 1, if if the water table lies at the base of the footing, so that means dw by df will be equal to 1, and from this chart rw will also be 1. Okay. So I was just trying I was just trying to show how to read this graph. Okay, how to read this graph. So I hope you have understood. So now let me just go back to the question. So what is the question? So now there are some SPT values given at different depths, okay, at different elevations or depths. So this is a ultimate bearing capacity. So this is a bearing capacity problem, okay, and the breadth of the footing is 3 meter by 3 meter. This is square footing, so breadth is 3 meter. So influence zone is up to 2b. For bearing capacity problem, it is 2b, I believe. How much it is? For bearing capacity problem, it is 2b. So what is the b? B is 3 meter, that is 6 meter. From the base of the footing is the influence zone. One minute. Oh, I just wrote the opposite over here. For settlement case, actually, for settlement case, the influence zone is 2b, and for bearing capacity problem, it is b actually. So the influence zone, this is a bearing capacity problem. The influence zone is b from the base of the footing, that is 3 meter. Okay, so 3 meter from the base of the footing. So what is the total depth of the what is the total depth? Actually, see, if this is the footing, if this is the footing, and what is the depth of the footing given in the question? The depth of the footing is 1.5 meter below the ground surface. So depth of the footing is 1.5 meter below the ground surface, and the influence zone is 3 meter below the base of the footing. So what is the total depth? It is 3 plus 1.5 meter. That means 4.5 meter. So up to this depth, we need to just consider the SPT value. So see, up to 9 meter SPT value is given, right? Up to 9 meter SPT values are given. We need to consider up to 4.5. We need to consider up to 4.5. That means we need to just average out these values only. Up to this, up to 4.5, we need to find out the average SPT value. So what is the average SPT value? So what is the average SPT value up to 4.5 depth meter, 4.5 meter depth? That is 10 plus 20 plus 25 plus 27 plus 28 divided by 5. So see, all these values 10, 20, 25, 27, 28. So n average, SPT average is 10 plus 20 plus 25 plus 27 plus 28, okay, divided by 5. If you just calculate this, you will get SPT average is will be 22. Okay, if you just calculate, you will get n average to be 22. Okay, so now let us go back to the equation. So in the question, it is a circular footing, 3 meter by 3 meter. So now we have the values of all the parameters over here. So 1 by 3. What is n? N is the average SPT value, which is 22. Average SPT value is 22 square into B is 3 meter. And what is RW dash? It is given in the question. It is 0.65 and RW is 1. So RW dash is 0.65 plus 3 into 100 plus SPT value, average SPT value, which is 22, into DF. What is DF? The depth of the footing. The depth of the footing is 1 meter, 1.5 meter. And what is RW? RW is 1. It is given in the question. So RW is equal to 1. Now, if you calculate this equation, you will get net ultimate bearing capacity to be 1191 kilonewton per meter square. Okay, so this is the answer. What I did is that I have just incorporated all the values of all the parameters into this equation, and I have solved this equation. So the answer that comes out, it is 1191 kilonewton per meter square. So if you have any problem in this question, please let me know. One thing you must know, one thing you must remember, for settlement problem, the influence zone is 2b from the base of the footing, and for bearing capacity problems, you must consider influence zone. The depth of the influence zone should be b from the base of the footing. Okay, so for settlement case, the influence zone will be 2b from the base of the footing, and for bearing capacity problems, the influence zone will be b from the base of the footing. Okay, you just need to remember this. So now let me just move on to the next problem. So this is the problem number 4. A raft foundation of dimensions 10 meter by 20 meter is placed on a layered clay soil. So here we have the a raft foundation. We have the dimensions. So breadth is 10 meter and length is 20 meter, placed on a layered clay soil. Okay, so first let me just draw the problem once. So we have a footing raft foundation. Um, Raft foundation is not like that actually. This is a raft. There are several footing. There are several columns over here like this. Okay, so this is a raft foundation of dimensions 10 meter by 20 meter. Suppose so. This is the breadth. Breadth is 10 meter. So the breadth is 10 meter, placed on a layered clay soil. Layered clay soil, and the raft is placed at a depth of 2 meter below the ground surface. Okay, so depth, it is 2 meter below the ground surface. Fine. The raft is subjected to a total load of 10,000 kilonewton. So load is coming from here, 10,000 kilonewton. Okay. And what else? The foundation soil has two layers, layer 1 and layer 2. The properties are given over here. The depth of the first layer is given. It is from ground surface from 0 to 14 meter. Okay, so up to this. Suppose 14 meter. This is layer 1, the first layer. Okay, and these are the properties. And layer 2 is from 14 meter to 20 meter. From 14 meter to 20 meter. That is, the thickness is 6 meters. So this is the layer 2. And the properties are given. Hard stratum is observed at a depth of 20 meter from the ground surface. That is, after the second layer, there is hard surface, a hard stratum, hard soil. The water table is at a depth of 2 meter below the ground surface. So water table is at the base of the footing. The base of the footing is at 2 meter below the ground surface, and the water table is also at a depth of 2 meter below the ground surface. So that means the water table is at the base of the footing. And here we have been asked to find out the bearing capacity using Skempton bearing capacity equation. Okay, and after that we need to find out the applied factor of safety in terms of bearing capacity. Okay, so we need to find out bearing capacity using Skempton's formula. Fine, so let me just check out the influence zone once. So this is a settlement problem, right? No, this is a bearing capacity problem. So for bearing capacity problem, the influence zone is how much? It is B. It is depth B from the base of the footing. So what is the depth? What is B actually? The breadth of the footing is 10 meter. So that means influence zone is 10 meter below this footing. Suppose it is over here. Influence zone is up to here. Okay, that is 12 meter from the top, 10 meter below the base of the footing, and 12 meter from the top of the ground, from the ground surface. Okay, so that means the influence zone is within the first layer, right? So influence zone is not invading into the second layer. So that means we need to consider only the first layer. Okay, so up to this zone, up to this line, it is the influence zone. Okay, from the base of the footing. So now let me just go back to the problem. So we need to use Skempton bearing capacity equation. So what is the Skempton bearing capacity equation? So Skempton bearing capacity equation is so Skempton bearing capacity. So Skempton equation for net ultimate bearing capacity, that is QNU, for net ultimate bearing capacity Skempton. It is just CNC. Okay, it is just CNC. Now this NC is different over here. We need to use a Skempton equation to find out the NC. So what is NC? So what is Skempton's NC? It is for a rectangular raft. Actually, it is a raft for a rectangular footing. It is 5 into 1 plus 0.2 into B by L into 1 plus 0.2 into df by B, and this one should be less than or equal to 9. So now we have all the values of all the parameters. So what is the breadth of the footing? The breadth of the footing is 10 meter and the length is 20 meter. So breadth of the footing is 10 meter, length is 20 meter, and what is the depth of the footing? The depth of the footing is 2 meter. So the depth of the footing is 2 meter, and what is the breadth? It is 10 meter. Now if you just calculate this, you will get NC is equal to 5.72. If you calculate this, you will get NC to be 5.72, and this is obviously less than 9. So there is no problem. Now just we need to find out QNU, that is the net ultimate bearing capacity. It is CNC, and since the influence zone is not invading the second layer, we just need to use the cohesion value of the first layer. So what is the underlying cohesion of the first layer? It is given over here. it is 25 kilonewton per meter square, CU. So this one will be QNU equal to CNC. C is 25 kilonewton per meter square and NC will be 5.72. 5.72. If you calculate this, you will get Nu will be equal to 143 kilonewton per meter square. Okay. So now what is the second part of this question? The second part is determine the applied factor of safety in terms of bearing capacity. So you need to find out the factor of safety. So you need to find out the factor of safety. So this one is the net ultimate bearing capacity, that is the the maximum load, maximum stress the foundation can carry, maximum pressure apart from the overburden pressure actually. So overburden pressure is getting deducted from the ultimate bearing capacity, and in that way you will get a net ultimate. This one is net ultimate. So no overburden pressure is involved in this, only the stress due to the load that the foundation is carrying. Okay, only the stress that is occurring due to the load that the foundation is carrying. So we need to find out factor of safety. So this is the maximum stress that the foundation can carry due to additional loads. Okay, that is 143 kilonewton per meter square. And what is the current load? And what is the current additional load that the raft is carrying? It is 10,000 kilonewton. Okay, so that means what is the stress? What will be the stress? It will be 10,000 divided by 10 and 20. So before carrying out factor of safety, we need to find out the stress that the raft is currently carrying. So 10,000 load is the load that the raft is currently carrying, and the area of the raft is, and the length and breadth of the raft is 10 and 20. So what will be the area? It will be 10 and 10 multiplied by 20. So this one will give us the current stress that the raft is experiencing. So what will be the current stress? It is 50 kilonewton per meter square. And what is the maximum stress or pressure that the raft can carry? It is 143 kilonewton per meter square. So what will be the factor of safety? Factor of safety will be QNU by Q only. So QNU is 143 kilonewton per meter square and Q is 50 kilonewton per meter square. If you calculate this, you will get the factor of safety to be 2.86. If you so the factor of safety is 2.86. So this is the answer of this question, of the second part of the question. So if you have any problem in this question, if you have any doubt, please let me know. If you have any doubt, please let me know. Or else I'll proceed to the next question. So I believe you have all understood what is happening in this question. Also, there are some question in the chat box. Let me just go through that. So the first question is, please can we say that the width of foundation has no effect on bearing capacity if the water table is far below? Yes, obviously. Obviously, if the water table is uh, if the water table is below the influence zone, obviously there will be no effect. If the correction factors are 1, if the correction factors, if you suppose, if you calculate the correction factors and if you get the correction factors to be greater than 1, that means it will, if the correction factors cannot be greater than 1, right? So that means if you somehow you get the, somehow suppose your depth of the water table is such that the correction factor is coming greater than 1, it will not happen. So that means if your depth is such that the correction factor in that case is greater than 1, that means the water table will have no effect. Correction factor will simply be 1. Okay. So, and if that means if the depth of the water table is way below the base of the foundation, that means it will have no effect on the bearing capacity or settlement. Okay. So, and the next one is with respect to the first question, can you say the width of the foundation has no effect? Oh yeah, I have already so I have already answered that question. With respect to the first question, can you say that the width of the foundation has no effect on the bearing capacity? Or yes, obviously. And please, how do you calculate the correction factors if not given in the question? I have just explained you using the graphs. The graphs will be given. Okay. So let me just proceed to the next question. So question number 5. What is the question number 5? It is determine the consolidation settlement of the raft of question number 4. Okay. The previous question. After applying all the possible correction factors, the pore water and the depth correction factors is zero point 0.7 and 0.94 respectively, neglect the immediate settlement. So we need to find out the consolidation settlement of the previous question. Okay. So previous question, we need to find out the consolidation settlement of this raft of question number 4. So in question number 4, we have found out the Skempton bearing capacity, the Skempton's net ultimate bearing capacity. So in this question number 5, we have been asked to find out the consolidation settlement of that raft. Okay. So let me just draw that problem once. Suppose this is the raft and the width of the raft is 10 meter. The width of the raft is 10 meter. The raft is placed at a depth of 2 meter below the ground surface. The raft is 2 meter below the ground surface. And let me just look at the diagram once. And the depth of the water table is also at the base of the ground surface, that is at 2 meter. Here lies the water table. Yes, the water table is at the depth of 2 meter below the ground surface. And what are the other things that are given? The thickness of the layers are given. The thickness of the first layer is 14 meter, and the thickness of the second layer is 6 meter. Right? 14 from 20. So this is the first layer actually. First layer, the thickness is 14 meter, and the thickness of the second layer is 6 meter. Yes, thickness of the second layer is 6 meter from 14 meter to 20 meter. Okay, and all the values of all the and the properties, the soil parameters are given over here. That is the unit weights and the compression index and the undent cohesion, initial void ratio, and water table, yeah, and the unit weight of water. Everything is given over here. Okay, we just need to find out the consolidation settlement. So in this problem, what we need to do actually? In this problem, the heart stratum is over here. The heart stratum is below this 6 meter. So what we need to do? This one, see, earlier we solved a similar problem. This problem, okay? The problem is quite similar to this problem. This is the problem number 2 actually. We need to find out the stress distribution at a point at a depth, at a certain depth. We need to find out the stress distribution due to the additional load that the raft is carrying. We need to find out the effective overburden pressure at that point, and after incorporating all those into the consolidation equation, we will, if we incorporate all the parameters, if we incorporate all those things into the consolidation equation and calculate the equation, we will get the consolidation settlement, as simple as that. So earlier in that problem, we considered 2:1 stress distribution. That means 2 vertical is to 1 horizontal. We will use the same stress distribution ratio in this question also. Okay. So this thickness, how much is this thickness? It is 12 meter, and this one is 6 meter. Okay. So we need to find out the settlements at the middle of these layers. Okay. So what will be the thickness of this portion of the half portion? It is 6 meter, and this portion will be 3 meter. At the middle, okay, we need to find out the set. We need to consider this actually, half of the thickness of the first layer and the second layer. We need to find out, initially we need to find out the stress distribution at these points. Suppose this point is A, this point is B. We need to find out the overburden pressures at this point, and also we need to find out the stress at this 2 point, the additional stress that is causing due to the additional load. Okay, so we need to find out the additional stress and also the effective overburden pressure at point A, at point B. So let us just calculate all those things. So what will be the effective overburden pressure at point A? So what will be the effective overburden pressure at point A? This is the depth of the water table, and this height is 2 meter. So 2 meter into gamma bulk. So let me just check the unit weights. So for layer 1, gamma sat is this and gamma bulk is this. So that means for layer 1, gamma bulk is this and gamma sat is this. So gamma bulk is 16 and gamma bulk and gamma sat is 18. Okay, so 16. So that means the effective overburden pressure. So at point A, effective overburden pressure will be 2 into P is equal to 2 into what is the gamma bulk? It is 16. 2 into 16 plus what is the thickness of this layer? It is, and what is the thickness of the submerged portion? It's 6 meter. And what is the saturated unit weight of that portion? Saturated unit is 18. So what is the submerged unit weight? Submerged unit weight is 18 minus 10 into the thickness. How much is the thickness? Thickness is, how much is the, How much is the thickness? The thickness, this portion, yes, this. How much is the thickness? It is 6 meter, right? So into 6, the submerged portion. So if you calculate this, 2 into 16 plus saturated into 2 into 16 plus gamma sat minus gamma w, that is the submerged unit weight, into the submerged unit, so the submerged portion thickness, that is 6 meter. You will get the effective overburden pressure at point A, which is 80 kilonewton per meter square. And what is the additional stress that is acting at this point if we consider 2:1 stress distribution ratio? 2:1 stress distribution ratio means, see, here the thickness is 6, so that means, suppose this thickness is 6, so that means this one will be a half of 6. If this one is 2, this is 1, 2:1, that means this will be 3 and this will be also 3. So what is the new breadth of this raft, of the effective breadth, actually, not new depth, the effective depth at point A? What is effective breadth actually? So what is the effective breadth of the raft at point A, at this, not point, actually at a depth of 6 meter? So 6 meter at the, it is the half of the layer 1. So the effective breadth is, the breadth of the raft is 10 meter, this thickness is 6 meter, and the stress distribution ratio is 2:1. So that means if this is 6, this one is 3. If this is 6, this one is 3, and up from this point to this point it is 10 meter. So total effective breadth will be 10 plus 3 plus 3. So effective breadth will be 10 plus 3 plus 3, that is 16 meter. Okay, same thing in case of length. So initial length was 20 meter. So initial length was 20 meter. So that means effective length will be 20 plus 3 plus 3. Am I right? So it will be 26. So what is the additional stress that is acting at a depth of 6 meter below the base of the footing? It is, what is the additional load? Additional load is 1000 kilonewton. So it will be 10,000 kilonewton. So it will be 10,000 divided by this 16 and 16 multiplied by 26, which is the effective area. So if you calculate this, the additional stress will be 24 kilonewton per meter square. Okay. So now we have found out the additional stress and effective overburden pressure at this point, at point A. Now we need to find out the effective overburden pressure and the additional stress that is acting due to 10,000 kilonewton at point B. Okay. So for point B, what is the effective overburden pressure? So at point B, what is the effective overburden pressure? Let me look at the diagram. So for this portion it is 2 meter, the thickness is 2 meter, and also the unit weight, the bulk unit weight, what is the bulk unit weight of the layer 1? It is 16. So 2 into 16 for the top portion. So 2 into 16 plus this whole portion. So the length, so the thickness of this whole portion is 12 meter. So 12 into submerged. So 12 into the saturated unit weight of the layer 1 is 18. So submerged will be 18 minus 10. plus at point B. Okay, so from what is this is where the layer 1 ends. Okay, so from this up to this is the half of layer 2. So what is the this particular depth? This is 3 meter. That is the half of depth of the layer 2 depth, half of layer 2 depth. So it is 3 meter. So we must find out the effective stress and the additional stress that the additional load is causing at point B. So the depth of point B from the top of the surface, the depth of the point B from top of the surface is how much? It is uh, 6 meter plus, so it is 3 meter. Sorry, this whole thing is 6 meter. This is 3 meter. So it is 14, 14 plus 3. Okay, 17 meter. So now what is this thickness? It is 3 meter. And what is the unit weight of this submerged portion? So saturated unit weight of layer B is saturated unit weight of layer B is 20. 20 is saturated. So what will be the submerged? 20 minus 10. So 20 minus 10 into this thickness is 3 meters. So into 3. So this is the effective overburden pressure at point B. So if you calculate this, you will get effective overburden pressure at point B. At point B, this one is PB. Let me denote it like this. If you calculate this, you will get PB to be 158 kilonewton per meter square. Now, if you consider stress distribution of 2 vertical is to 1 horizontal, you need to consider that to find out the additional stress that is causing due to 10,000 kilonewton at point B. So same thing is happening over here. So we need to find out the effective breadth and effective length at point B at this point. So so 12. So see, how much is this depth? Stress distribution will be like this from the base of the footing up to this point up to point B. See this carefully. Stress distribution will be like this. Let me just draw it once again over here. The footing is like this. This is layer 1, this is layer 2. This is point B, suppose. Stress distribution will be like this, right? 2 vertical is to 1 horizontal. Fine. So what is the breadth of the footing? Breadth of the footing is 10 meter. So this one is 10 meter. And what is the depth of B from the base of the footing? What is the depth of B from the base of the footing? It is 12 plus 3. See, this one is 2 meter, and from top here where the layer 1 ends, the depth of the layer 1 is 14 meter, and the rest is 6 meter, right? The layer 2, depth of the layer 2 is 6 meter. So 2 meter is the depth of the footing. So that means from base of the footing, so from this point, it is 12 meter. This one is 12 meter. That is 14 minus 2 from the base of the footing. So 14 minus 2, it is 12 meter plus 3 meter. So 12 plus 3 is 15 meter. So depth, so 0.5. So depth of point B is 15 meter from the base of the footing. Okay, so this length, so this thing, so this depth is 15 meter from the base of the footing. So now if this one is 15 meter, this one will be how much? 7.5. This one will also be 7.5. So what is the new effective breadth? It is 10 plus 7.5 plus 7.5. Okay, so that means 10 plus 15. Please let me know if you have any doubt in this. If you have any doubt in this concept, please let me know. And same way, we are finding out the effective length. In the previous question, we also did the same thing. So what was the original length? Original length of question number 4. What was the original length? Original length was 20 meter. So what will be the effective length? The effective length will be 20 plus 15. The stress distribution is similar. Only in place of breadth there will be length. So 15 plus 7.5 plus 7.5. So that means 20 plus 15. Okay, so new effective breadth will be 25 and effective length will be 35. So now we need to find out the additional stress at point B. So del P at point B will be 10,000 kilonewton divided by 25 and 35. 25 multiplied by 35. If you calculate this, you will get the additional stress at point B is equal to 11.43 kilonewton per meter. One thing have you observed? The point A, which is much shallower than the point B, it is obvious the depth of point A is much lesser from the ground surface. Obviously, the depth of point A is much lesser. It is closer to the base of the footing. The depth of the point A is closer to the base of the footing, and point B is much deeper than point A. So the additional load that is being caused due to 10,000 kilonewton is much more in case of point A. At point A, the additional stress is much higher. At point A, the additional stress which is being caused due to 10,000 kilonewton is much higher because it is much shallower. It is nearer to the base of the footing. But the effective overburden pressure is lower. See, in case of point B, the effective overburden pressure obviously will be higher because it is at a very much depth, and the additional stress is lower than the point A because it is much deeper than point A. So the stress which is being caused due to 10,000 kilonewton is lower than at point A. Is lower in case of point B than point A. So now we have found out all the parameters. Now we just need to put everything into the equation. So we have the effective overburden pressure at point A. We have additional stress that is being caused due to 10,000 kilonewton at point A, and we also have the effective overburden pressure at point B, and we also have the additional stress as at point B. So we need to find out the consolidation settlement. So how we will find out the consolidation settlement? We will find out the total consolidation settlement. In order to find out the total consolidation settlement of the raft, we need to find out consolidation settlement for the top layer as well as for the second layer, and then we need to sum it up. So what is the equation? The equation is S is CC, that is the compression index, divided 1 plus E0. H is the thickness of the layer into log of P0, that is the effective overburden pressure, plus del P, the additional pressure, divided by P0, that is the overburden pressure. This is the equation. We need to just calculate for both the layers and we need to sum it up. So what will be the total consolidation settlement? So what is the compression index for the first layer? Compression index for the first layer is 0.212. And what is the initial void ratio? It is 0.5. So Cc divided by 1 plus E0. So Cc is 0.12 and E0 is 0.5 into what is the thickness of the first layer from the base of the footing. From the base of the footing, what this thickness is 12 meter. This thickness, the this thickness, uh, the thickness of the first layer from the ground surface is 14 meter. The depth of the footing is 2 meter. If we subtract 2 from 14, we will get 12. So thickness of the first layer from the depth of, from the base of the below the base of the footing, it is 12 meter into log of initial effective overburden pressure at point A, it is 80, and additional pressure at point A is 24. Is 24 divided by 80. This one is for layer 1, and for layer 2, what is the value of compression index and void ratio? Compression index is 0.08 and void ratio is 0.8 plus 0.08 Cc divided by 1 plus E0, 0.8 into what is the thickness of the second layer? Thickness of the second layer, it is 6 meter. So into 6 into log of effective overburden pressure at point B, it is 158 kilonewton per meter square plus additional stress 11.43 by 158. Now if you solve this equation, you will get the total consolidation settlement, which is 62 millimeter. So this is the answer. If you have any doubt in this question, please let me know. Here we are just calculating the consolidation settlement for layer 1 and layer 2. After that, we are just summing it up. Okay. Before that, we are finding out the effective overburden pressure at the middle points. At the middle points of layer 1 and layer 2, we are finding out the effective overburden pressure at those points and also the additional stress that is being caused due to the additional load of 10,000 kilonewton. Okay. So after that, we have all the parameters of the soil, that is the compression index, void ratio, and the unit weights, etc. And after incorporating all those parameters into this equation, we are getting the total consolidation settlement. So I hope you guys don't have any problem in this question. So let me just move on to the next one. So this is the problem number 6. So the problem number 6 is a plate load test was conducted on a 30 centimeter square plate at a depth of 2 meter below the ground level on a sandy soil, which extends up to a great depth. Determine the settlement of foundation of 4 by 4 carrying a load of 1200 kilonewton placed at a depth of 2 meter below the ground surface. The settlement of the plate corresponding to 75 kPa load is 4 mm. The position of the water table is at a great depth. So for sand, actually, for sand, for sand, there is an equation, and for clay there is another equation for plate load test settlement. If you want to just extrapolate the plate load settlement, the settlement that you got from the plate load test, if you want to extrapolate that settlement to a footing, you need to use a particular formula for sandy soil, and for cohesive soil there is another one. So for sand, the formula is SF, that is the settlement for settlement of the original footing. Okay, settlement of the footing. SP is the settlement of the plate. B BF means the breadth of the footing. BP is the breadth of the plate plus 0.3 divided by breadth of the plate BF plus 0.3. So this is the equation. This is the plate load test equation for the source sandy soil actually. So using this equation, you can just extrapolate the plate load test settlement to a original foundation settlement. Okay. And for clay soil, there is another equation. For clay, the equation is SF, that is the foundation settlement. BF means the breadth of the footing. SP means the uh, plate settlement, and BP is the breadth of the plate. Okay. So this one is for sandy soil. This one is for clay soil. So in the question, the question, what is it? It is sandy soil. So we'll use this equation. Okay. So we need to find out the settlement of a 4 by 4 meter footing. Okay. Placed at a carrying a load of 1200 kilonewton. So okay. So see how much load the foundation is carrying. It is 1200 kilonewton. And the what is the breadth of the foundation, square foundation? It is a 4 by 4 foundation. So the foundation is 4 meter by 4 meter and it is carrying a load of 1200 kilonewton. Okay. So that means what is the stress acting on the foundation? It is 1200 by 4 by 4, that is 75 kilonewton per meter square or 75 kPa. And for the 75 kPa, the plate settlement is 4 millimeter. Okay, so that means we have the plate settlement, we know the size of plate, we know the size of footing. Okay, so we just need to find out the foundation settlement. Okay, so let us just incorporate all the values into that equation. So let me just write it down. So SF is equal to SP BF by BP plus 0.3 BF plus 0.3. Okay. In this equation, it is 0.3. That means this equation, all the breaths will be in meter. Okay, all the breaths will be in meter. If in place of 0.3, if in place of 0.3, if there was 30, in that case we would have to use breadth. We have to use breadth of the footing and plate in terms of centimeters. Okay, so in this case, here it is 0.3, so that means the breadth of the plate and the breadth of the footing will be in meters. So now let me just incorporate the values of all the parameters. So SP, what is the size of the plate? So size of the plate is 30 centimeters. So that means 30 centimeter means 0.3. Sorry, this is not the size of plate. Sorry, this is the settlement of the plate. Sorry, so what is the settlement of the plate? The settlement of the plate corresponds to 75 kPa is 4 millimeter. Okay, so 4 millimeter. If you put this settlement in 4 millimeter in terms of millimeter, you will get the settlement of footing in terms of millimeters. Obviously, because this is a ratio actually. This is a ratio. All the units are same. So SP is 4 millimeter, that is the settlement of the plate. What is the value of BF? That is the breadth of the footing. Breadth of the footing is 4 meter. Breadth of the What is the breadth of the plate? Breadth of the plate is 30 centimeter. That means 0.3 meter. What is the breadth of the plate is 0.3 meter plus 0.3. And what is the breadth of the footing? It is 4 meter plus 0.3 square. If you solve this, you will get SF to be the foundation settlement. After calculating this, the foundation settlement will be 13.85 millimeters. Okay, so this is the answer. So if you have any doubt in this question, please let me know. If you have any doubt in this particular question, please let me know. So what is happening in this question? In this question, we after conducting a plate load test, after conducting a plate load test, here we got at 75 kPa the settlement of the plate was 4 millimeter. Okay, so we have been asked here to extrapolate that plate settlement to a foundation settlement. So the breadth of the foundation is 4 meter. That is, it is a square foundation, so breadth is 4 meter. So we have just extrapolated the 4 millimeter plate settlement to a foundation settlement. Okay, and the load acting at the plate and load acting on the plate and on the foundation should be same, obviously. Here 75 kPa is acting on the plate and corresponding settlement is 4 millimeter, and on the 4 meter by 4 meter footing 1200 kilonewton load was acting. So 1200 kilonewton means 1200 by 4 into 4, that means 75 kPa. So the stress, the pressure, so the pressure is same in both the cases. Okay, so in this way we have found out the foundation settlement by using plate load test. So now let us proceed to the next question. So two plate load tests were conducted at the level of a prototype foundation in the same cohesionless soil close to each other. The foundation data are given over here. The size of plate is given, load applied given, corresponding settlement is given, and size of the other plate is given, load is given, and corresponding settlement is also given. So if a square footing, so actually two plate load tests were conducted. Okay, so now if a square footing is to carry a load of 800 kilonewton, determine the required size of footing for the same settlement of 25 millimeter. Fine. So here two plate load tests were conducted at the same depth to that of the footing depth. So two plate load tests were conducted to the same depth level of a prototype foundation, of a original foundation. So the plate load tests, the result. So these are the sizes of the plates, and corresponding load and settlements are given. And here we have been asked that if a square footing is to carry a 800 kilonewton load, determine the required size of footing for the same settlement of 25 millimeter. Okay, so you need to find out the size of the footing. So in such problem, So Q, that is the load that is acting, that is the load that is acting, Q, can be written as AP, no, sorry, AM plus PN. A is the area of the footing, P is the perimeter of the footing, and M and N are constants. Okay, this is a way of solving such problems, solving such this particular problem. If you get this particular problem, this type of problem, you will follow this type of the steps which I am going to show. So first you need to assume this Q equal to AM plus PN. Okay, A is the area of the footing, P is the perimeter of the footing. Okay, this is the assume this equation. Okay, so if you have such plate load test results, and if you are asked to find out the breadth of the footing or settlement of the footing of a footing using the plate load test result, you will use this process. Okay, so I am showing you how to solve such problem. So this is the equation that we will assume Q equal to AM plus PN. A is the area, P is the perimeter. So for first case, so for this one, for zero point 0.6 by 0.6 plate load, for zero point 0.6 and for 0.6 by 0.6 plate. So what will be Q? What is the Q? Q, the load is acting, the load is 75 kilonewton. So 75, this is the Q. What is area? Area is 0.6 into 0.6, 0.6 into 0.6 into M. M is a constant plus P. What is the perimeter of the square plate? Is 4 into 0.6, 4 into 0.6 into N. Suppose this is equation 1. Okay. Now we must write the same equation for the second case. So for the second case, the breadth of the plate is 0.75 and the Q is 100 kilonewton. So 100, Q is 100, and area is 0.75 into 0.75 into M. M is the constant, and the perimeter, what is the perimeter? It is 4 into 0.75 plus 4 into 0.75 into N. Okay, this is the equation 2. Now this is equation 2. Okay, so the first equation will come out to be 0.36 M plus 2.4 N is equal to 75. So this is the first equation, and the second equation is 0.563 M plus 3N is equal to 100. So this one is the second equation. Okay, I have just solved, I have just multiplied and put it over here, wrote it over here. So I have just multiplied this and this, and this, and after multiplying I have written the equations over here. So now if you solve this equation, solve these two equations, if you just solve these two equations using calculator or by hand, you will get the value of M and N to be, the value of M will be 55.35 and value of N will be 22.95. Okay, this will be the value of M and N. Okay, so now we have been asked to find out the required size, that is the required size of a square footing, that is the breadth of a square footing, the size of a square footing to carry a load of 800 kilonewton for the same settlement of 25 millimeter. So that means, so since the plate load test settlement and the footing settlement is same, so we can write it like this: Q equal to AP plus, sorry, AM plus PN. So here in this case, what is Q? Q is 800. 800 equal to what is the value of A, that is area of the footing. Area of the footing. We don't know the size of the footing because we have been asked to find out the size of the footing. So suppose it is B. If the breadth of the square footing is B, so that means what is the area? Area is B square, and we know the value of N. It is 55.35 plus we know the perimeter. What is the perimeter? It is 4B, right? If the breadth of the footing is B, then the perimeter is 4B. We know the value of N. What is the value of N? It is 22.95. Okay. So this one will be 55.35 B square plus 91.8 B, and this 800 comes over here, minus 800 equal to 0. Now if you solve this quadratic equation, you will get the value of B to be 3.1 meter. If you solve this quadratic equation, you will get the value of B, which is 3.1 meter. So that means the size of the square plate is 3.1 meter by 3.1 meter. This is the required size of the square footing. Okay. So this one is the answer, and this is the last question. So the last question is, according to IS 1904/1978, the permissible maximum settlement of raft foundation for RCC structure. So this is only a one word on this. So here the maximum permissible settlement according to 1904/1978 for raft foundation, it is 75 millimeter. It is according to the code. Okay. So that's all. So if you have any problem in today, if you have faced any doubt, please let me know. If you have any problem, if you have faced any problems till now, please let me know. In any question you may tell. You may also post your question in the discussion forum, or else you can also mail me. I will answer your mails. Please let me know if you have faced any problems till now.
Sir, please the fruitly question in my mail, sir.
Huh? What? Can you please repeat your question?
Sir, please send the every question, solving question in my mail ID, sir.
Do one thing, please post your doubts in the discussion forum, and yeah, and all the slides, actually these all the slides will be available in the NPTEL site. uh, See, all the questions that I have solved over here, all the answers you will get in the NPTEL site. All the slides, today's slide will be made available on the NPTEL site, and also the recorded version of this session will also be available. Okay, so there is no need to worry.
Okay, sir.
Okay, okay. So that is all for today. So see you in the next session. So goodbye for today.
Sir, when will be next session is coming?
Next week on Tuesday. Okay, from 6 p.m. to 8 p.m.
Okay, sir.
Okay, okay, okay. Goodbye.
Okay, sir. Bye, sir. Good night, sir.
Good night.